Example 3. Show that the function f y equals 3x minus 8 over x minus 3 is a self-inverse function, first by reference to its graph and then using algebra. So here you see the concepts of the self-inverse function mentioned again. So what is a self-inverse function? You may remember from the prior lesson that the self-inverse function is such a function whose graph is symmetrical with respect to the diagonal of the first and third quadrant. It means that the function can be understood or can be taken as self-inverse if the inverse of the function is the same as the function itself. So if you reflect it in this line, in this green line, you should obtain the same function as before. This function is the inverse of itself. So the function is self-inverse if f inverse of x equals f of x. This is the property of the self-inverse function. It has to be its own inverse. Now we have to show using the graph that this function here is a self-inverse function. So let me copy the function formula here, y equals 3x minus 8 over x minus 3. Now I'll try to work with this formula to show that it really is symmetrical with respect to the y equals x axis. So therefore, what I try now to do is to get its graph. Therefore, I will try to transform it to the form k over x minus m plus n. This is what I want to do. So to do that, let me start by taking out number 3 in front of those numbers in the numerator. So I'll take out 3, so it's x minus 8/3, okay, divided by x minus 3. Now I try to replicate negative 3 in the numerator, so 3 is in front of the fraction, and here I have x minus 3 plus 3 minus 8/3 divided by x minus 3. So you may remember that this thing here is a zero inconvenient form. Y equals then 3 times x minus 3, and here we have x minus 3. I'll put it in a pair of brackets, and the second number is 3 minus 8/3. So 3 in thirds is 27. Well, it's 9/3, sorry, it's 9 over 3, 9/3, minus 8/3 is 1/3, so it's plus 1/3. Now I can multiply, well, I can now do the following. I can split this into two fractions, so it's like x minus 3 over x minus 3 plus 1/3 over x minus 3. This one is unity, so this is just 1, so it's 3 times 1 plus 1/3 over x minus 3. And when I multiply it out by 3, what I get is the following. It's 3 plus 1 over x minus 3. Okay, so this is the formula of the function f, written in a convenient form that is helpful when we want to sketch its graph. So what we already know, that this number here, number 3, is m. Therefore, it's the value for which the function is not defined also corresponds to its vertical asymptote. And incidentally, it's this vertical line here passing through 3 of the x-axis. So it's x equals 3, it's the vertical asymptote. Moreover, this number here is n, which represents the vertical translation of the original function. So it should be also the horizontal asymptote. So this number here, 3, represents the horizontal asymptote y equals 3. Now, this function f has to do with the function f sub 0, which is simply 1 over y equals 1 over x. Okay, 1 over x. 1 over x, like you can read it out from this formula here. So what the graph of the function 1 over x would be? Its asymptotes would be the x and y axis, and it would pass through this point and this point. So this would be the 1 over x function like that. What we need to do is to shift it now by 3 units to the right and through 3 units upwards to get the graph of the function f itself. So this point with coordinates 1, 1 is shifted here to this position, and this one is shifted to this new position. Moreover, we know that these lines here are the new asymptotes, so the function should take this form, like you can see here. It's very crude what I'm sketching, but you get the idea, hopefully. So this is the function itself. Now, I have prepared the graph of this function in advance for you in GeoGebra. So this is the graph, and you see that really it's shifted to its asymptotes are cross at the point with coordinates 3 and 3. So the whole function is the function f sub 0 shifted by 3 and 3 to the right and upwards. And you see, which is the most important thing, that the graph itself is symmetrical with respect to this green diagonal of the first and third quadrant. So really, this is in line with this result here, obtained using the crude method of trying to transform the function from the rational function to the function of this form, which is also the rational function, but it's easier for us to read and to understand the position of the graph. So this is for the first part. Now, since the graph is symmetrical with respect to y equals x, then it means that the function should be self-inverse. Now, let us do it the other way. We are now going to use we are going to use algebra to show that the graph or the function itself is self-inverse. To do that, what we need to do is actually take, sorry, let me choose this. Let me write the formula, but when I write it, after doing that, I will just interchange x and y coordinates. So now I do the interchange. So I exchange x and y like you see here. And what I obtain is the following. X equals 3y minus 8 over y minus 3. And the whole, what remains here is to express y from this formula. So let me multiply it by y minus 3. So I get x times y minus 3 equals 3y minus 8. Now xy minus 3x equals 3y minus 8. Now let me combine the terms containing y on one side. Let me shift perhaps this to this side and this term to this one. So this can be done using the algebraic operation represented by subtracting 3y from both sides and adding 3x. So what I get appears here. So I get xy minus 3y equals 3x minus 8. Now let me take y out in front of brackets. So it's x minus 3 equals 3x minus 8. And now let me divide finally by x minus 3. And I obtain the answer y equals 3x minus 8 over x minus 3. Remember, this is the function f inverse. Okay, so this is the formula of the inverse function to the function f itself. But it's 3x minus 8 over x minus 3. If you compare it with the formula of the function f, which was here, I have copied it from the text of the exercise, you see that this and this is identical. So if the function is its own inverse, if the inverse of the function has the identical formula to the formula of the original function, then of course the function can be proclaimed to be self-inverse. And this is what we wanted to do in this exercise.